Okay, hello everyone. Let's get into part 4 of D.1 on gravitational fields. This part deals with orbital motion, or as it implies, the motion of something orbiting a smaller object, usually orbiting a much bigger object as a result of gravity. So we're going to talk a lot about satellites when we're talking about orbital motion. And so our first question is, what is a satellite? The gravitational force between two bodies provides the centripetal force necessary to make a smaller body orbit a much larger mass. So gravitational fields and gravitational force allow this phenomenon, and that smaller body is considered a satellite of the larger body. So to think about why satellites do what they do, why they move around an object versus falling straight into it, you can think about Newton's famous thought experiment where he imagined a cannon on top of a very, very tall mountain, and here I've drawn my approximation of Earth and a cannon on top of I drew a tower. So if this cannon fires a cannonball and the cannonball comes out kind of slow, then you can imagine it making a path, maybe something like this, and then hitting the Earth. If the cannon fires the cannonball a little bit faster, then you can imagine the path making maybe something a little bit more like this, and then even faster than that, maybe the path would look something like this. And you can imagine we can continue going around until the cannon fires the cannonball so fast that it's the rate at which it falls essentially matches the curvature of the Earth. And then as long as nothing's around to slow the cannonball down, then we can assume that it would that the cannonball would just continue to go round and round the Earth, and it would achieve an orbit. It would become a satellite. And we have satellites now. We have artificial satellites. These would be our own satellites that we make and launch into space. So we have artificial satellite. We have our moon, which is a natural satellite. So those are mainly the two types of satellites. Things that are already up there without our doing, that would be a natural satellite, versus the satellites that we release, which is an artificial satellite. When it comes to the motion of a satellite or the motion of a body orbiting another one, we're going to revisit some things from A.2, which involved circular motion, centrifugal motion. So here we have a smaller body, which we'll call lowercase m, orbiting a larger body, which is uppercase M. And what's necessary to create the circular motion is a centrifugal force. Centrifugal meaning, centripetal force. A centripetal meaning center seeking. So not centrifugal, centripetal. That would be a force coming toward from the smaller object to the larger object, like that. And then according to Newton's third law, then we're going to have the same amount of force going back the other way. Okay, so those forces are in force pairs, and the motion its instantaneous velocity is going to be going perpendicular to that force. This would be this object's instantaneous velocity, meaning the velocity it is at that second, knowing of course that it's going to continue around the path. Okay. So that's sort of the mechanics of orbital motion. Also useful to note that there will be a radius of the orbital motion. And revisiting some concepts from circular motion from A.2, we know that centripetal acceleration is equal to v squared over r. So the speed squared divided by the radius gives us centripetal acceleration, which means that since we're talking gravitational force, then centripetal acceleration, which we know of as the acceleration of gravity, or the gravitational field strength, is v squared over r. So now we've got a new expression that gives us, gravitational field strength if we know speed and radius, but probably more usefully is if we know the gravitational field strength at some distance away from a planet, then we can tell how fast an object must go to orbit the planet. Notice that the necessary speed of a satellite does not depend on its mass. We've already determined that objects of different masses accelerate with the same amount of acceleration when they're falling. So a satellite, as long as it has to orbit a given planet at a given distance, it doesn't matter how much mass a satellite has. It has to be traveling at a certain speed. So if we know a satellite's speed and the radius of its orbit, then we can also determine the time period for an orbit. So time period is, remember how long it takes to complete one orbit. So we're going to use the idea that speed or velocity is equal to distance divided by time. The distance or circumference of a circle is going to be 2 pi times its radius. This is an r. If you know the radius of an orbit, we can figure out the distance around, or the circumference, and that divided by the period or the total time will give us the speed. So let's put these things together and answer question D.1.8. So D.1.8 says, determine the orbital speed and time period of a satellite that orbits the Earth at a distance which is as far above the surface as the center of the Earth is below. Okay, so we've got the Earth, and we've got some satellite that orbits the Earth. It says at a distance which is as far above the surface as the center of Earth is below. So we can imagine our satellite. Let's do a purple satellite. We can imagine our satellite maybe here, and there's a certain radius from the center of the Earth to its surface, and then that radius again, this would be r, this would be r again, would be the how far this this satellite is above the surface of the Earth. And we're trying to determine the orbital speed and the time period. So to get the orbital speed, we'll probably use this expression, g is equal to v squared over r. Well, we don't know g. Well, we know g is 1/4 of what it was before. So here's what we're going to use. We're going to use g equals v squared over r. Now we don't know g. This is what we're trying to figure out. We're trying to figure out speed. We know the radius. We don't know g, at least not directly, but we can figure it out. We know that this orbit, this satellite, is twice as far away from the surface of the Earth as, say, someone standing on the Earth. Okay, so someone standing on the surface is going to be just 1 r away from center of the Earth, and we know this satellite is 2 r's away. So we know this satellite is twice as far. Well, we know gravity and gravitational field strength follow an inverse square law. So if we're twice the distance away, 2r, then that's going to give us 1/4 g. So we know the gravitational field strength for the satellite. It's g divided by 4, which is equal to, getting a calculator, it's going to be 9.8. So let's see, 9.8 divided by 4 is 2, we'll go with 2.45. We'll keep 3 significant figures for now, just to put a guard digit in there. So 2.45 newtons per kilogram, or meters per second squared. Now with that, we can figure out how fast our satellite must be going. So we can use, let's see, v, so v squared equals g times r, or v equals the square root of gr when we solve for g. So v is equal to the square root of g, which we said is 2.45 newtons per kilogram, times r. Now r is 2 Earth radii. And we know the radius of the Earth is 6.4 times 10 to the 6 meters. No, we need to go 2 of those. 2 times 6.4 times 10 to the 6 meters. And so plugging that into our calculator, so do that along with me while I do this here. So 2.45 times 2 times 6.4 10 to the 6th equals 5,600, or 5.6 times 10 to the 3 meters per second. Okay, that's our orbital speed. That's how fast this satellite's going to need to go in order to stay in orbit. We're also asked to figure out the time period. So there we're going to use t is equal to, different expression. V is equal to 2 pi r over t, which means t is going to equal 2 pi r over v, which is equal to 2 times pi times r. R is, once again, 2 times 6.4 times 10 to the 6 meters, all over the velocity, which we said is 5.6 times 10 to the 3 meters per second. So it looks like our meters are going to cancel out. We're going to have 1 over seconds, which is equal to seconds, which is the right unit for time period. So we're going to get, let's see, setting this up in the calculator, we have 2 pi times 2 times 6.4 times 10 to the 6 meters divided by 5.6 times 10 to the 3 meters per second equals, it should be 1.4 times 10 to the 10 to the 4 seconds. Now, if you look at this example in the book, you'll see that their answer is 7.2 times 10 to the 3 seconds. That is not correct, because we need to be using 2 times 6.4 times 10 to the 6 meters. I think they only used, in the book, they just used 1 times 6.4 times 10 to the 6 meters, but we're actually twice that distance from the center of the Earth. So anyway, let me know if you have any questions. That's it for now, and I will talk to you soon. Thanks.